Thank you so much, Steve. I appreciate you included at least a little bit of expressivity into your talk, to not make me look that silly. But anyway, thanks so much. Super interesting. Yeah, I just wanna, without further ado, give the stage to Diana, on her talk, and yeah, afterwards, we're gonna do some housekeeping, and then we're gonna jump into the discussion part. All right.
All right, thank you. Hopefully I'll be able to share my screen. So let me see if this works. All right.
Looks good.
Yeah,
Thank you.
it's
Yeah.
working. All right, let's go. All right, so hi everyone. Thank you for inviting me uh, to share a little bit of my work with this group. So this talk is going to focus on this paper about understanding the feature structure interplay for graph neural networks. It's a work I developed in the scope of my PhD, but just so that you have a bit of an idea about my progress. So I started my studies in Portugal with a master's in bioengineering. Then I did a little bit of work as a researcher with Fraunhofer Portugal Laicos, mainly on applied research, a lot with the time series processing. And then I decided I wanted to dive a little bit deeper in AI models, and I decided to follow a PhD studies in Belgium, where I currently am. This is how my problem with GNN started. And it made me research into a lot of what was going on there. And currently, I am so I finished my PhD, and I am an AI researcher at IMEC, where I'm conducting research about multimodal AI architectures for new sensor modalities. Okay, so off to what you are actually maybe interested in. About this presentation, I'm going to keep it quite short. Maybe we can discuss it a little bit later if needed. So just a little bit of context and motivation to get us started. Then I'm going to dive right into some of the results that I think are more interesting about this work. And then afterwards for some key insights I think can be useful. And first of all, I know that here people have like a background in graphs, most likely in graph representation learning as well. But I wanted to talk a little bit of how I got stranded with this question of investigating the feature structure interplay. And it's because when I was doing my research, one thing that I found is that GNNs actually have a very inconsistent performance trends across the universe of graph problems. And there's been plenty of research into it, but what I managed to conclude actually is that we were deriving increasingly more complex models. And I have here a bit of a benchmark just to give us an overview of what I am considering these types of inconsistent trends. So for example, so I have here these data sets organized by increasing homophily, just because it's a metric that it's very quickly associated sometimes with the performance of GNNs, even though probably, as most of you are aware, there are some problems with this metric as well. But just for the sake of understanding this, one of the patterns that we observe when we look at a benchmark results like this is that sometimes there is no one single method that systematically outperforms the other, not even for benchmarks with, let's say, equivalent levels of homophily or and another even more striking pattern, at least for what I was interested, is that sometimes the simplest form of GCNs actually performs on par with the state-of-the-art methods. And sometimes this structure agnostic MLP even performs on par with state-of-the-art methods. And so I was interested in seeing what is going on here. And this led us to study a little bit the dual nature of the smoothing component of GNN. So as we know, the graph has two components, right? So we start with the graph as it is, and then we typically populate it with feature vectors. Now in here, for simplicity, I'm only considering feature vectors on the nodes, and I'm going to consider node classification throughout. But what I am interested also in seeing here is that because GNNs focus on this aggregation mechanism, and it's difficult to break the pattern of to escape this, we also have a phenomena associated to this aggregation mechanism, which is the smoothing. Now, the smoothing, ideally, if we are using a GNN, what we want to see is something a little bit like what we see here. So, for example, if you consider that in my x-axis I have these propagation steps, this is just because I tried to use the simplest form of GNNs that I could, so the SGC, but well, essentially you can think about them as steps as well. Ideally, what we would like to find would be a behavior that is a little bit like this. So we have a stage that throughout the learning process, that is this stage of beneficial smoothing. Now, because we also know that if we keep aggregating, we will enter this over smoothing phase, the curve of what we might expect that happens looks a little bit like this. Now, what we actually find sometimes is that there is a chance that there are some graphs for which this actually, the curve does not look as nice. So we might not even enter this regime of beneficial smoothing. I missed something in my explanation. So for me to consider this beneficial smoothing, I am looking at that baseline of an MLP, which is feature only. So it's that red baseline. And what I am considering beneficial smoothing here is when our GNN actually leads to better predictions than an MLP baseline. So, and if I go below that MLP baseline, I'm already considering that I entered an excessive smoothing phase all the way until over smoothing defined by this random chance of classification. So if on one hand, sometimes we enter this very interesting beneficial smoothing that might be a good motivation for us to use a GNN to solve a problem, some other times we seem to not enter that regime at all. And this led us to inspect a little bit what was going on between these two, the dynamics of these two components of feature and structure. And this was our method. So since we were trying to explain a phenomena, we were also trying to create the simplest method possible so that we can look at what is happening very well. And the method that we created basically relies on the following. So we take an original graph, which can be an artificial, so a synthetic graph, or it can be one of the benchmarks. And we are going to derive a set of mutations of that graph. One of them, the first of them, is what we call the random connectivity one. So what is going to happen here is just that I'm going to shuffle all of my connections, and now they're supposed to be meaningless to solve my downstream task. The second of them is that I'm going to randomize over all of the features of my nodes. So now there is a mismatch between the label of my node and the features that are associated with that node. But in this case, I keep the connectivity as original. And finally, the bottom one is just essentially, it will be our sanity check. It will be just everything is destroyed. So we are supposed to not see anything interesting happening here. And I'm not going over all of the results that are in the paper. So I'm going to jump a little bit ahead to the parts that can be more interesting for discussion. And in here, what we will see in this figure, so we will have as baseline still the MLP with the original features and the MLP on the random features. So essentially, again, just random chance of classification for the baseline of our problem. And then we will have the results for running a GNN on the original graph and on each of the mutations. And ideally, what we would like to see would be something like this. So for example, if I run my GNN on the original graph, I am indeed better than using an MLP alone, and performing a mutation on each of the components, either the connectivity or the feature information, will derive a drop in performance that is still a little bit better than fully random. So this is what we would essentially expect to see. Now we ran this for several different benchmarks, for several different models, and I'm going to pinpoint some striking conclusions. So for example, for some data sets, we identified that sometimes the original and the random connectivity are actually equivalent. And this is something that can strike us as surprising, but it's part of the findings of this study that we should keep in the back of our heads. But also we found evidence of like two strong flavors of models here. One of which is this the models that have a strong smoothing bias. So we identify significant drops of performance every time that we destroy each of the components. But we found yet another flavor, which are these models that are rather feature preserving. And for these models, what we identify is an equivalent performance between the random connectivity and the MLP. So these are the two flavors of models that we could actually identify with our experiments. Now, this is from a purely, a very visual way of seeing this, but we actually wanted to condense this a little bit further and try to extrapolate if we could actually see this from a different point of view. And we tried to actually condense this into these two different metrics. So we tried to create a metric for assessing the structure contribution and another one for assessing the feature contribution. These metrics are meant to be quite straightforward, and the idea goes a little bit like this. For the structure contribution, we have a term that is associated with a performance drop caused by destroying the structure, and another term that is associated with the performance gains over random chance when we only keep the original structure, but the features are randomized. And they are essentially equivalent. So for the feature contribution, we do something similar. So it's the performance gains that we have by keeping the features and the performance drop caused by destroying the features. And we wanted to see if these metrics were actually good predictors of what we wanted to see. So in here, we have a ground truth that is essentially the absolute gains of using a GNN versus an MLP. So this is essentially our ground truth. And we want to see if these two metrics are good enough to predict this output. So we run just a simple regression analysis, and we identified that these metrics can actually be a good predictor of the advantage of using a GNN versus just an MLP, especially if we consider them with interaction coefficient. So not just if we think about them as an addictive, with addictive power, but if we consider that they actually interact with each other. Good. So now we are here. We have two metrics, one for the structure contribution, another one for the feature contribution. We have also an interaction coefficient. And with this, we managed to get quite a good fit in predicting what are the absolute gains of using a GNN versus just an MLP. But we wanted to see even further how this interaction manifests. So in here, in this plot, what is plotted is essentially the ground truth, so these absolute gains, versus the structure contribution. And the feature contribution, we divided it essentially in two groups. A group where it is above or equal median and a group where it is below. These can be immediately thought as problems with good feature component or problems with a bad fit or very noisy feature component. And what we see is actually that when feature contribution is very high, the contribution of the structure becomes almost irrelevant. And we have this sort of flat line that we see here. But on the other hand, when we actually see low feature contribution, we do see the outstanding gains of using a GNN to solve the problem. And this is a bit, the duality is a bit an evidence of those two flavors that I was discussing before. So bottom line, the key insights that this work brought forth is that, well, we identified sort of this sweet spot for applying GNNs. And it is when this local smoothing effect that we know that they have is actually appropriate for denoising the feature signals by using the structure component. And also we presented evidence of this measurable trade-off between what we see as two flavors of models, right? In modern GNN architectures, we have models that are rather feature preserving and models that are rather reliant on their strong smoothing bias. So as future research, what we think would be important for the community to focus on is that we believe we should move from beyond these fixed architectural biases that have been the main drive of current GNN architectures, all the way towards developing architectures that effectively adapt to this structural feature dynamics. And in particular, we believe that appropriate ways of doing this could be to explore more rich co-attention mechanisms, more rich adaptive aggregation mechanisms that can modulate how much I rely on my neighborhood or not per task, per problem that I'm trying to solve with a GNN. And good, I believe that this is not the room for Q&A, that we are going now to the breakout room, so maybe this doesn't apply. I will give you back the floor.
All right, thank you so much. Yes, let's please thank the speakers one more time. Thank you, thank you, thank you. And also I'd ask Pascal to stop the recording.